Okay, so let's look at some Booklet 3 electricity questions. So we've got a series circuit shown in the diagram. We've got a 6-volt power source and 50 and 100 ohm resistance in series. What's the potential difference between A and B? Well, we've got two resistors in series, so we're looking at a potential divider, so we can use the potential divider expression to calculate that. So an additional 100 ohm resistor is connected between the 50 and the cells, so it's added in series. What's the PD now? Well, we still can use a potential divider because we've still got resistors in series. We just need to add the 100 to the bottom line and we get a new lower potential difference of 2.4. The 100 ohm resistor is now connected in parallel with the first 100 ohm resistor. What is the potential difference now? So what I'm going to do is I'm going to calculate the combined resistance of those two, which, because they're identical, will just be half of one of them, so 50 ohms, and then we can stick that in place in the potential divider equation, so now we get, essentially, it's split in half, 3 volts. Okay, so a potential divider is made of a 4 kilo ohm and a 6 kilo ohm resistor connected in series with a 20 volt supply. Draw a diagram of the arrangement and what 4 values of potential difference can be tapped off. So this is a diagram of the setup, the two in series with 20 volt power supply. And then, so if we put a voltmeter across the 4 kilo ohm resistor, we'd get a potential difference of 8 volts. If we put it across the 6K, we're going to get 12 volts. So they had to give 20. We could also put a voltmeter across the power source, which would give us a potential difference of 20 volts. And we could also put it between things with no potential difference at all and get a value of 0. So if, say, we put it between the cell and the first terminal of the 4K resistor, we'd get 0 volts because we assume there's minimal drop across the wires. So a student puts a 12 ohm variable resistor in series with a 6 volt battery, expecting to get a variable potential difference. The voltmeter is a high resistance digital multimeter. Explain why the circuit won't work. There are 2 reasons why this will not function as a variable resistor. The first one being we've got a voltmeter in series, and a voltmeter is an infinite resistor, so we're not going to get any current. So that's pretty useless for a start. And also the section with the variable resistor, because it's on its own, its potential difference has to be 6 volts, because it's the only component in the circuit, so its potential difference has to be 6 volts if we're ignoring the fact that there's no current or anything else. So they're kind of the 2 possible reasons we could come up with here. So in terms of a diagram that could work, first of all, we'd need to add in a wire like this. This is going to mean the current flows through the 12 ohm resistor, and that would mean we actually start dividing the potential between the sides of the potentiometer. So that could work, and quite often you see these with another resistor connected in series as well. That just makes sure your current doesn't spike too high, but it's the fact that we need the current going through the actual variable resistor that's important here. Okay, so B is the wiper of a 100 ohm rotary potentiometer. What's the full range of potential difference that can be tapped off between A and B? Okay, so let's put B at the maximum resistance and the minimum. That's how we're going to approach this. So if we put B on the minimum resistance, i.e. with no resistance, there will be no potential difference between A and B. If we put B so that the whole 100 ohm resistor is connected, then we're going to get a 3 volt potential difference here. So that's kind of our range of possible values we could, as I say, tap off. Okay, so we've got 2 potentiometers, both at their midpoints, it says. Find the potential difference recorded by a voltmeter of infinite resistance in each circuit. So essentially, we can do 2 calculations here. It's halfway, so we put half of the total number on the top line, and we get our 3 volts and 5 volts respectively. The digital voltmeter is replaced by a moving core voltmeter of resistance 500 ohms. Calculate the new readings. So let's do the one on the left first. So Remember, it's halfway, so there's 125 either side in the 250, and we've just put a 500 ohm resistor in parallel with that. So we can calculate the total resistance of the combination of those two. Then once we've done that, we can then put it into the potential divider equation. Our total resistance is now going to be slightly different. We've got the other 125 plus the 100 gives us 2.7 volts. If we do the same thing to the other circuit, we've got a 500 in parallel with a 50 because it's split in half. And then again, we then can work out what the split would be for the voltmeter, 8.4 volts. Okay, so a 100 ohm rotary potentiometer is connected to a 6 volt DC source with negligible internal resistance. The output required is 3 volts. The potentiometer is set using a high impedance digital voltmeter connected across its output terminals. And just for your information, as far as we're concerned, impedance is the same as resistance. Once we start looking at induction and capacitance, that's not true anymore. But for these type of circuits, impedance and resistance are the same thing. So a few minutes later, someone else checks the output reading using a moving core voltmeter with a resistance of 100 ohms. What happens now? Well, so if we're getting 3 volts output, that means there's 50 ohms on either side of the potentiometer, similar to what we've seen before. So if we've got 100 ohms in parallel with one of those 50s, we can get what the combined resistance is. And then once we've got that, we can put that into our potential divider equation, and we can see we're now going to get a 2.4 volt. So by having a non-infinite resistor, we can see we've decreased the voltmeter reading. Okay, so looking at some next questions, we're trying to put this in context. So here we're looking at controlling a robot arm. So the arm needs to be able to travel 180 degrees or 90 degrees either side of the vertical. So we've got a 3 kilo ohm rotary potentiometer. So the total resistance in our circuit is always going to be 3000 ohms, but how much of it is across the potential output potential difference is going to vary. Okay, so the potentiometer has a total angle of rotation of 300 to make sure we don't, essentially, the arm never goes off of the potentiometer. Okay, so that's our setup. What current flows through? Well, we know the total resistance and we know the potential difference, so we can calculate what the current is, 1 milliamp, and that's never going to change, but the way the potential difference splits will change. Okay, so if the robot arm is vertical, halfway through its possible movement, what is the potential difference? Well, it's going to be split equally either side, so it's going to be 1.5 volts. So if the arm moves through 10 degrees, how much does the output of the potentiometer change? Well, remember 300 degrees is 3000 ohms, so therefore 10 degrees change is going to be 100 ohms. So we could do this with either the maximum or the minimum, it doesn't make any difference. We can see we've got a change of 0.1 volts when we apply that. So then if the output potentiometer changes by 0.3 volts, what angle have we moved? Well, if 10 degrees is 0.1, that would mean 30 degrees is 0.3 because resistance increases or decreases linearly, it tells us. Okay, so now we're going to look at using an amplifier as a comparator. So just some background here. An amplifier essentially goes, okay, what value of potential is at my positive terminal, what value is at my negative terminal, finds the difference between those, and that tells the amplifier what to do. It amplifies the difference, and it typically amplifies, a lot of the ones we use amplify only positive potential differences, i.e. the positive terminal is higher than the negative. Okay, so in this case we're looking at illuminating an office, and we want the light intensity or the illumination to not go below 4000 lux, and we're going to use an LDR to achieve that. So at 400 lux, the LDR is 300 ohms, and if it gets brighter, the resistance falls. Okay, so the LDR is connected to a potential divider in series with a 1.5 kilo ohm resistance, making a potential divider, and we've got a 9 volt supply with no internal resistance. Okay, that's our setup. So what is the potential difference when the light level is 400 lux? Well, we're just using our potential divider equation here, fairly straightforward. A second potential divider with resistances of 5 kiloohms and 1 kiloohm is connected with the same supply. Show the potential difference across the 1 kiloohm resistor is the same as across the LDR. So again, using our potential divider equation, you don't even need to convert into ohms because they're all in kiloohms. So you can see it's also 1.5 volts. So what is the potential difference between A and B? Well, it's going to be the same. So if the potential difference across the LDR and the 1 kiloohm are both 1.5, it stands to reason that the potential difference across the 1.5 and the 5 are 7.5. So that we've got 9 at the top, loses 7.5, and they're both left with 1.5 potential at A. There. So we get a potential difference of 0 at this crossover condition when the light intensity is 400. So if the light gets dimmer, what happens to the potential difference between A and B? Well, it's going to get bigger. So, essentially it'll go above 0. So its potential difference across the LDR increases because its resistance has got bigger. That's what the potential divider equation really tells us. The potential A has to be higher if it's going to lose a bigger amount across the LDR. The potential of B hasn't been affected. We haven't changed anything in that circuit. So the potential difference between A and B is going to get bigger. Okay, so we've got this is where the amplifier comes in. So we've got A connected to its positive terminal, B connected to its negative terminal. And it says if its output is positive, it turns the lights on. So will the lights come on when the office falls below 400? So what we said previously, if once it dims below 400 lux, LDR resistance goes above 300, so we then at that point go, yes, that is going to turn on because the A is going to become bigger than B. So the positive terminal is bigger than the negative terminal, so its output is positive, and therefore the lights turn on. Because essentially what the amplifier does is it takes the positive value and it subtracts the negative value from it. So that would turn on. And that's important to remember for the next few questions. Modify the system to switch on a motor if the light level exceeds 2000 lux. The resistance of the light-dependent resistor is 80 ohms when the light level is 2000 lux. So here is my circuit that I'm going to use. We need to make sure the LDR to the 1000 ohm resistor ratio is replicated in the other circuit. So I've got 800 to 10 kilo ohms, for example, and typically these additional resistances are much bigger. And then this time you'll notice I've connected what we had A in the previous diagram, or the potential above the LDR, to the negative terminal and the other one to the positive terminal. So I've actually reversed the connections. And the reason we do that is because the potential is going to, above the LDR, is going to decrease as it gets brighter because its resistance gets smaller. So we need that one connected to the negative terminal so that we still have when we do the positive minus the negative, we still get a positive number, and therefore in this case the motor turns on. A typical handheld torch runs off two 1.5 volt cells, yet has a lamp rated at 2.5 volts, 0.5 amps. Explain how the potential difference across the lamp can actually be 2.4 volts as rated, and what is the internal resistance of each cell, supposing them to be identical. So we can work out how much potential difference there is across the internal resistances. So I'm going to call that V lost. So the output should be 3 volts, but the actual output is 2.5. So we must have lost 0.5 inside the cells. There are 2 of them, so we must have lost 0.25 in each, because they're identical. And then once we know the potential difference, we know the current, so we can figure out what the internal resistance is. It's 0.5 ohms. A typical car battery has an EMF of 12 volts and must provide a current of 80 amps. So the starter motor, so it must be pretty low resistance if we're going to get that higher current. So why must a car battery have very low internal resistance? If the internal resistance is 0.05 ohms, find the potential difference across the internal resistance when the starter motor is running. Why is starting the car with headlights on likely to affect their brightness? So first of all, if we're going to draw a current of 80 amps from 12 volts, we need a total resistance of 0.15 ohms. So if we would then, so that's the total resistance. If we put the internal resistance on the top line, we can see that the potential difference across the internal resistance is going to be 4 volts. So why do we need a low internal resistance? Well, we've just calculated the maximum resistance in the whole circuit is 0.15 ohms to get 80 amps. So if you have an internal resistance bigger than that value, the current will drop below the value needed to actually start the car. And that's one of the problems that happens as the car batteries get old. Their internal resistance increases and you actually lose the ability to start the motor and you need a new battery. Okay, so why is starting the car with the headlights on likely to affect their brightness? Well, anyone who's driven a car, you can turn the lights on without the engine being on because they could run off the battery. However, if you start directing current towards the starter motor, a smaller current is going to be going to the lights, so we'd expect them to dim during the startup process. Okay. Some school laboratories have an EHT ultra high tension power pack giving up to 300 volts. For safety, they're provided with a 50 mega ohm resistor in series. What is the maximum current able to be drawn from the supply? So we're going to do potential difference divided by resistance gives us a very small current. That's 60 microamps. Approximately what potential difference would there be across a torch bulb connected across such a supply? Well, we don't know anything about the bulb, so we're going to need to make an assumption. So I'm going to go with its resistance is about 100 ohms. You could obviously assume it's a variety of different things. And therefore, once we multiply that by the current, we can see we get a 6 millivolt potential difference across the torch bulb. So we're getting very, very small values. Okay, so a student experimenting with a solar cell connects a 1000 ohm voltmeter across it and observes a potential difference of 10 volts. Use a different extremely high resistance digital voltmeter. The reading is larger, 1.2 volts. What is the difference? So the really high resistance digital voltmeter is actually measuring the EMF. The 1000 ohm voltmeter is measuring what we call the terminal voltage. So with the low resistance voltmeter, we've created a circuit where current can flow, and if current can flow, we're going to get a PD across the internal resistance, decreasing the terminal voltage. And we can actually use these values to work out what the internal resistance is. So the general equation you see linking this is EMF is terminal voltage plus current times the internal resistance. We know the EMF, we know the terminal voltage, so we know that IR equals 0.2. So if we're going to get internal resistance, we need to figure out what the current is. But we know the terminal voltage and the resistance, so we can figure out the current, and using those two values gives us an internal resistance of 200 ohms, and that completes this circuitry video.